many people here have played Robotron? All right. Okay. Cool. All right. So, if anybody doesn't know what Robotron is, it's right over here. When you talk post-mortem, it's kind of this morbid term. There's kind of a stench in the air, and it's like, what went wrong, what went right. Often it's, and I've been in this business for 37 years. So many projects, so much more went wrong than went right. But it is a wonderful learning experience. Really, really cool when you spend like 2 or 3 years spilling your guts out for something you're super passionate about, and then it turns into a disaster. But often the fault is with other people. Isn't that how it always works? It's like there's other guys, and a lot of times they're wearing suits. Anyway, Robotron was not one of those projects. It was kind of a magical experience. We did the game in 6 months, and just kind of everything turned out right. It was, the feeling was amazing when we put it out. And I guess it was kind of like the feeling the Candy Crush guys had when they crushed gamers' wallets for $1 billion recently. Pretty cool. Not to take anything away from them, but we hit that mark 30 years ago with Robotron. 1 quarter at a time. Here's a little Robotron if anybody hasn't seen it. Okay, there's some pretty cool, intense action there. But now this game doesn't exist yet. So we just finished Defender and Stargate. Spent about 18 months on the side-scrolling space shooter genre. Really, really fun times, crazy games. But at any point, you always kind of you kind of burn yourself on something, and you want to do something completely different. And so wanted to try something new, try a new genre, and really the only thing to start out with was that robots are really cool. And so I was inspired by a couple other games. There was a game called Chase on the Commodore PET. How many people had Commodore PETs? Oh my God, this is scary. This was a character-based machine, had a really cool cassette drive, and the Chase was this turn-based game that you were, I forget what letter you were. I think the robots were pi signs or something, and there was little asterisks that were mines, and you tried to just lure the robots into mines. There was no shooting in the game. Kind of a cool game, kind of fun, kind of an inspiration there. The other inspiration was this dynamite game known as Berserk. Yeah! Let's hear it for Berserk. I mean, wow. Al McNeil was the team leader on that game, and it was really awesome. I remember playing it. I was still finishing up Defender in like September of 1980, and this game Berserk came in the arcade, and the robots. It had like this joystick, like whoa, man, 8-way joystick. You went through these mazes. Everything killed you. It was just like total death trap, and just got totally addicted to this game, and was like still trying to make Defender a fun game at this point. And I was like really depressed. I was like, God, this guy's just totally kicking my ass. And but I got kind of frustrated with the controls. The single joystick was tough to use because you had to kind of move where you were firing. There were so many tight points in this game. The walls even killed you. That it was a tough game, but it was really awesome. And I guess kind of like Flappy Bird. I mean, we just all want to have our asses kicked, and Berserk really kicked our asses. Here's a little gameplay of Berserk. some really, really cool sounds. That's actually the first video game that talked right here. And really neat. And you went on to more and more mazes, intruder alert, etc. Other influences of this game, which I guess was known as Robot Wars, initially were obviously Defender and Stargate, the really awesome audio system we had, kind of the theme of humans, of having someone in the game that was your friend rather than just killing everything that was an enemy. The software and hardware system from Defender, and kind of bringing that into a robot genre with the dual joystick control, kind of a key innovation. And thinking about the frustration I was having playing Berserk, where I had to move where I was firing. The weird thing was there was a mode in Berserk, if you held down the fire button, you would stop and then the joystick would fire. And so, like, I was like, whoa, like the joystick fired, I moved. Dude, let's just have two joysticks. One fires and one moves. I mean, really, really awesome. Okay, we had, let's talk about video hardware here. This was state-of-the-art 1981. 1 megahertz Motorola 6809. This thing rocked. Anybody program on a 6809? Okay, two guys. I feel sorry for you. No. 32 kilobytes of RAM, 48 kilobytes of DRAM. You had your battery backdraft memory, 320 by 240 video resolution, 16 colors. One of the cool things about the system was it was a bitmap architecture, which has become a standard feature on all video games today. The bitmap utilized just a memory map where pixels were written into memory, and in the case of Defender and Stargate, by a processor. And this was different than the standard architecture of the day, which was known as a character map. The character map basically had a series of codes we called a matrix of characters, or sometimes called postage stamps, and then sprites, which were used for the motion objects. The problem with character map systems was, if you look at like Pac-Man and other games of that genre, was that you could only have a few motion objects on the screen at a time, or there was a limitation of how many sprites you could have on a horizontal line. So this bitmap architecture allowed you to overcome these limitations and have incredible, anything you could write to the screen, you could display any number of motion objects, and also you enabled particle effects, which was really, really awesome. The other thing we had was a 19-inch RGB CRT. And I love that glow, that CRT glow. We kind of got built-in anti-aliasing with that phosphor glow. But the other really cool thing about our CRTs is they're very fast. Actually, they're much faster than LCD displays. I think almost all LCD displays have a frame lag of at least 32 milliseconds because they're doing scaling, anti-aliasing of their outputs. So when the video goes in, 32 milliseconds later, for the fastest LCDs, it comes out. The CRT, the video goes in, the video comes out instantly into the beam. So really, it was kind of cool for Twitch gaming because you had very, very fast response. The Robotron hardware also had a single frame buffer. This was really cool because you didn't need, memory was very expensive, so you only could afford a single buffer. The bummer was that if you didn't watch how you wrote things to the screen, you'd get this tearing, where a screen would be half updated, and you would see a screen that was half of an old screen and half of a new screen, and you get kind of a tearing line. You could do some clever things. We did some clever things with object sorting to make sure this never happened. But the other cool thing about a single frame system, again, there's less delay. Today's systems, most are double or sometimes even triple buffer systems, which, again, add frame lag. If you're running at 60 hertz, you're talking 16 milliseconds more for each frame of buffering you have, which, again, kind of bogs out the response. The player, from the joystick to the video, you're adding more and more lag frames. The hardware at 16 colors. And then here was a really cool thing we had on the Robotron system, which was one of the first graphics coprocessors. We called it a bit blitter back in the day. Now it's known as a GPU. This sucker could do 1 megapixels per second, which was pretty awesome in 1982. Today, I guess they're talking about 100 gigapixels a second, so we weren't quite there yet. This did 2D XY block transfers. It had this really cool thing where it could write transparency, where a transparent object, a transparent pixel, was coded with a 0 code, and that pixel would not be written into the video's RAM. So you would avoid doing a read, modify, write. You could just write the active live pixels and basically double your bandwidth. Kind of a neat thing. A bummer was the GPU and the CPU shared the same address and data buses. So when the GPU and CPU were running, when the GPU was running, the CPU was not running, and that kind of sucked. Here's a picture of the hardware. Kind of like the Matrix, everything really was just a big battery. That's up in the upper left. That was the battery backup. You see the DRAM in the lower left corner, processor in the lower middle there. Okay, let's talk audio hardware. We had, it was a very basic system. The audio consisted of a CPU and a digital analog converter. Really, no hardware whatsoever, really. It was just like you had to make the sound with software. A whole 128 bytes of RAM and 2 kilobytes of programmed data ROM, very generous. 8-bit DAC. So the audio system, which incidentally turned out software, it was so hard to generate sounds in software that we really had to limit it to a monophonic system. So Robotron can only make one sound at a time. And so there was an elaborate priority scheme to make sure the most important sound was coming out to the player at any time. And so every sound had priorities, and they had uninterruptible periods, interruptible periods, trying to make sure that always the most important sound would get to the player, because the game could only make one sound at a time. The cool thing about this was whatever sound was playing was always at 11. So that was pretty awesome. So you look at sound, it's just a string of numbers, really. It's just a mathematical linear function string of numbers, and hopefully that sounds cool. Now, classic games, they're generally had hardware, square wave and, oscillators and white noise generators. They used this particular, I think it was some GI chip, I forget what it was, AY, whatever it was. Modern games use digital recording, so you can just record any sound you want. Makes things a lot easier, and you can do anything you want. Unfortunately, the 2 kilobytes we had could only store a fraction of a second. So that wasn't going to work unless every sound was like... Back in 1981 at Williams, we had to write our own sounds. And so we did software sound synthesis, where we would write... we just imagine sounds, imagine mathematical functions, write white noise generators using shift registers, exclusive ORs, maybe mod functions. We wrote pink noise generators, which is kind of cool. It's kind of mellow. We had wavetable synthesizers, and some of the coolest sounds were square wave modulation effects. There was this cool routine called Variwave that kind of made a lot of these weird space sounds. And kind of the cool thing was to save memory, all these sounds were parameterized, and you'd use about, it was about 8 bytes, I think, could characterize a sound. And sometimes just the coolest sounds ever were achieved by just typing in random numbers to one of these parameterized generators. In fact, I think the start sound is when you just set everything to 0. That was pretty awesome. Here's the hardware. You got your amplifiers on the right, and your ROM there with a little circular thing there, CPU to the left. Okay, let's talk game software in 1981. Really, there wasn't a hell of a lot to talk about, really. No high-level languages, unless you wanted to program in BASIC, which really kind of sucked. And with the memory limitations, you really couldn't do much. There were no real operating systems, no Windows. thank God. It was, I mean, Windows, you know, if we'd have been using Windows back then, I don't think anything would have been created that would have been functional. No APIs, no middleware, no tools, no Photoshop, Maya. Basically, everything was written in machine language, and you kind of just did your own stuff. But kind of the cool thing was that if you were kind of a megalomaniac, control freak programmer, which a lot of programmers are, this was like paradise. You just wrote everything yourself, and you knew what was going on. Sometimes it was quicker just to write a operating system than to learn how to use some crazy ass API with a 400-page manual. So it was a roll your own type thing. So the software system was kind of cool. We had data structures, actually, if you can believe it. And we used a linked list, dynamically allocated linked lists. And the cool thing about these linked lists was you would have a free list and you'd have an active list. And you'd only have to process those say, processes or objects that were active. And so you didn't have to spend a lot of CPU cycles cycling through massive arrays where most of the things were inactive. So save a little CPU time. There was also a process list. There was your global variables, of course, which I guess I don't even know if they exist anymore. They were cool, created a lot of bugs, but things happened quick. There was the process list was one of these linked lists, free and active. Then there was there was a multi-processing operating system. This was pretty cool, multitasking, multiprocessing. It was cooperative multitasking, up to 120 processes, just limited by memory. And the cool thing was about cooperative multitasking, it made things very, very simple. But if you had a rogue process, it kind of sucked. If somebody was out there bogging down, using all your real time, or somebody went into a infinite loop, it kind of drug the system down to zero. But since you wrote everything, you could figure it out. And then obviously there was the object list, free and active object list there, linked list there. Let's take a look at the object structure. We had a link to the next object, which was null, 0, if there was the end of the list or a null list. The picture, what picture we were displaying, upper left screen coordinates, world coordinates, velocities, all those good things, the collision routine that you were going to go to if you had a collision, some other stuff, 180 objects, pretty cool. Here was a process list, very similar. You link the address where you woke up a process, the time for sleeping. So processes basically would sleep for a certain amount of frames. Everything was processed on a frame basis. So they would wake up, go execute, and then go to sleep again. And you had local data storage for each process. So you could have say a robot process that was shared by the same code was, you could have 100 robots executing the same code because they all had their own local variables. Here's the process routine. I think this is the coolest code in the whole game right here. It would dispatch processes in 17 microseconds. I don't think Windows 8 can do this with a 3 gigahertz processor. It was about 20 bytes of code. You loaded your active list. It was null. You exited. Otherwise, you decrement your sleep time, and then jump to that process, execute the process. The process then would execute a nap macro. And macros were kind of this really cool thing where you could create kind of like high-level instructions that were just a series of assembly language instructions. And so you had this nap macro, which you load the sleep time, jump to the wake-up address, and jump back to, it would jump to the sleep processing, which jump over to sleep, and then you'd go and process the next, you'd store the sleep time and the address of the program counter to be woken up at, and then you would jump and go hit the other process. So it's about, I don't know, maybe 20 bytes. Pretty kick-ass little kernel here. We were very, very proud of this one. Okay, the main software loop You had a screen refresh at 60 hertz. We were very, very, very strict about that. The problem is when your video starts degrading to 30 hertz, or you start jumping back 30 to 60, everything starts getting kind of blurry and vibrating and kind of sucked. So we really wanted to have that 60 hertz. In order to process the screen, in order to throw the objects out of the screen, out to the screen RAM with the graphics processing unit, again, since we had a single buffer system, we had to worry about tearing. And so we had two interrupts, one at the top of the screen, one at the middle of the screen. And when you were at the middle of the screen, you would write the top of the screen. And when you were at the top of the screen, you'd write the bottom of the screen. And that way, we'd never get tearing. The objects were in a sorted fashion, and it was a nice system. Every now and then, it might get overloaded, but very, very rarely. Every frame, you'd dispatch the process list. You do the collision process to detect collisions, and then if you had any time left over, you'd sort the object list to keep the objects in order for writing to the screen. And then wait for the frame sync. So everything was synced up at 60 hertz. Collision detection was very, very simple. You checked box collision. If the two boxes collided, you had a collision, you try to fail really fast. So you would check the left coordinate of an object against the rightmost coordinate of another object. And if the rightmost coordinate of one object was to the left of the leftmost coordinate of another object, then there was no collision. And so you would fail on all four parameters, fail very quickly. And this was kind of the core collision routine that executed that code. It was a pretty nifty little 20 or 30 byte routine. Okay, let's talk about the Robotron story. Enough of this code. We're thinking about the human legacy, what we're leaving our planet with here, pollution, climate change. We have this wonderful environmental things that we do. We construct parking lots, which are wonderful for the ecology. We have nuclear bombs. We got wars. We got nuclear wars, mass extinctions. We're selfish. We're lazy, and we're not really good at sticking to diets either. So really, we kind of suck. And as humans, we realize these shortcomings. So our ambition is to create something that's better than that doesn't have all these things. And so we want to create the Robotrons. We want to create a perfect species that doesn't have all these problems, that we replace the imperfect with the perfect. Robotrons work 24/7. No human relations. No holidays. No whining. Pretty awesome stuff. And I do apologize. The language is kind of sexist there. And I think if women had created Robotrons, they would be much more inclusive and also perhaps nurturing. So things could have happened differently, but I guess what happened happened. How are the robots going to get so smart? Well, we have Moore's law. We're all familiar with that, where machine intelligence is doubling every 2 or 3 years, and it's been doing this for, 50 years now. And we're kind of seeing this now. Machines are, with this evolution, moving much more rapidly than human evolution. They're getting pretty smart. And as humans, I would really love to evolve like a sixth finger to handle those Xbox One controllers, and that might take 1 million years of evolution to achieve that. Natural selection is very, very slow, but with robot evolution, with machine evolution, it's kind of like it's intelligent design. Really, we're perfecting. Generations are taking place more and more rapidly, and then now we're using machines to help us design machines. Soon, machines will be designing machines. And at this point, we reach von Neumann's singularity, where we all kind of get just sucked up into the cloud. And there's some real utopianism out there right now where futurists are saying, you know what, we will suck our brain up into the cloud and be able to live forever, and have our consciousness forever. And that's pretty cool, but I wonder, though, if we have this cloud intelligence that's so incredible, why would they want to waste bandwidth on humans? So really, I think it's survival of the smartest, and you are not it. So, guided by their infallible logic, the Robotrons conclude the human race is inefficient and therefore must be destroyed. And so that's kind of the backstory. Let's talk about the design philosophy. Games today, we have the gigahertz, we have the gigabytes, we have incredible richness of creativity. I mean, last night at the rewards, they were talking about basically we could do anything we envision, do anything we want. Pretty much CG quality stuff out there. The classic arcade games, not so much. We have, probably 1/100,000th of the AV resources. A few thousand pixels versus gigapixels. Square waves, white noise versus symphony orchestras. The classic arcade is all about gameplay. That's really all we had. We couldn't dazzle them with our graphical brilliance. So it's about gameplay, play mechanics, tweaking. This was before Miley Cyrus. Challenge, difficulty ramping, balance. And it was kind of the cool thing there was kind of this hardcore scene in the arcade. We wanted to kind of have this long-term hero play where a expert gamer could kind of reach a plateau of amazing levels of skill and have the game be able to give him, challenge waves and relief waves and kind of ride this roller coaster for hours, maybe even days, playing the game. And this guy would kind of be your hero, and he would be written up in the National Enquirer or something. And then all the other players would want to become that hero, a very aspirational type hardcore play. And you really wanted to go along. Unfortunately, a lot of the classic arcade games fell into the mold of, like level 1 was easy, level 2 was medium, level 3, you're dead. Really wanted to avoid that. Wanted to have this kind of amazing, at the edge of human skill play. And back then, the design philosophy was a little different, but it was certainly was not the Hollywood AAA top-down script thing, which we see in the AAA titles today. Basically, you spend months, you script out your game design, you script out your action, your graphics, your art style, everything. You spend years implementing. You get a lot of little people. They implement this. Then you try it out, and if it sucks, hopefully it wasn't your money. But this actually works for amazing AAA titles today, sequels, known genres, experienced teams, and so we see this formula work terrifically. But it's not too good for indie teams or small teams. So for small teams, kind of the game jammy thing, which is what it was back in the arcade. It was all about kind of an interactive design where you start with a minimum playable design, play it, improve it, and then repeat it until it's fun. And so it was a very interactive process, and a game could evolve into something that was totally different than the original intention, kind of seeking out the fun as opposed to seeking out the script. This was a team. Myself, Larry DeMar there, and we were programmers, so that was kind of our thing, and so it created this programmer-centric design philosophy. Very limited art resources. I do apologize for the programmer art in Robotron, but I guess it worked. But it was the inspiration of kind of programmer-centric design it's kind of like a carpenter. If a carpenter has a hammer, everything starts looking like a nail. And so to a programmer, everything starts looking like an algorithm, And so basically the idea was to create algorithms to automate generation of levels, to automate the enemy dynamics, and utilizing some really good random number generation to create kind of a randomness and a freshness within a range that was cool, so you could keep the game fresh, you could keep it interesting for many, 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 many plays. So when you were developing this kind of interactive process, you needed a very fast turnaround. This is important, and it was really cool. In 1981, just as we were starting this project, they came out with this really, really cool machine. It was called an IBM PC, and it was like, oh my God! I went down to the computer store and like, this is going to be awesome. This is going to be the solution to everything, and this is what happened. The thing was it was like ridiculously overpriced. It had like these floppy disks, this crappy 16-bit Intel chip, no 68,000. I mean, what was up with that? I mean, it was pretty clear this thing would never catch on. And unfortunately, the Macintosh was still years in the future. So what did we do? So we looked around at other computer systems available, and we found that the real system of the future was the Gimmicks 6809. And this was the rockin' development system. 1 megahertz 6809, 56 kilobytes of RAM, a couple of dual floppies. I mean, these things, enormous capacity. This was the programmer's dream system. And the software, as we found, the software systems were almost non-existent. So we had to write our own text editor, and we really optimized these to all be memory resident. So all the text routine, text editor, and all the code had to be resident in memory. So in order to maximize that capacity, there was a tendency not to comment too much on your code because it kind of took up those bytes, and so you got this. In effect, even using tabs was expensive. So it created, it was self-documenting code. We called it. It was pretty cool. The other thing we wanted to do to make it turnaround time faster, because to remake the entire system would take a half an hour or an hour. These floppy disks, it was insane. So we created this modular system where the code was broken into maybe about 10 or 15 modules that were maybe 1 to 2 kilobytes, maybe 500 lines of code, maybe for each character in the game, different functionalities. And when you changed the module, we had them all load at absolute locations. All memory references were absolutely referenced. It was like a vector table at the beginning of a module that would have all references all within that module at fixed memory locations. So you didn't have to do linking. You didn't have to do anything to the other modules. You could just alter the module, reassemble that, and load it back into memory. So this created really, really fast turnaround times. It was really awesome. And then we had a debugger, which you could patch to tweak the thing. Also had single-step capability, which is great to find your stupid crashes. Okay. Talk about the game mechanic of Robotron. Robotron is a game of confinement. And it's interesting. Like, games really are about limitations. And where Defender and Stargate were games of like the freedom of flight, to go to have a world that was multiple screens flying around at massive velocities. This Robotron you're confined, you're very slow, you're trapped on that screen. You start in the center of the screen, you're surrounded on all sides, and really the only thing you have going for you is the dual joystick control. So you have this kind of fight or flight thing. And with the dual joysticks, you can fight and you can flight. You can fight and flight at the same time because you can retreat and fire at the enemy. So you're not restricted to fight or flight. So that was pretty cool. Anyway, the end result is like this total sensory overload where everything's coming from all sides, and you have all these cool decisions to make. Game design, kind of finishing up the story. Why are you there? I always think like in a game, you have to know why you're there, what you're doing. And so you are basically the last hope. You're the hero. You're the last hope. You have to stop the Robotrons. Somehow there was some kind of genetic engineering back in 1981, and it was kind of cool. And I guess it worked. And the other element that kind of pulling at the heartstrings of the player was the last human family. Bring in the human element. You're just not going out on a parched earth strategy. You are getting emotional about the last human family, saving them. So this kind of interactive design process, it started out with a first prototype. And, there's only a finite amount of time. So you always start with the easiest things first. And the easiest thing was an electrode. It really didn't do anything. It just sat there and killed you if you touched it. So that was the first Robotron enemy. It was very successfully implemented. The next thing, that really wasn't enough of a game, though, so we had to try to find some fun there. So then we came up with the grunts. I guess they were known as the Ground Roving Unit Network Terminators. And I think this was before Arnold Schwarzenegger, I'll have you know. Now, these Robotrons had a very minimal IQ, and which is kind of odd, because in the story, the Robotrons are more intelligent than man. And somehow the first Robotron is really, really fucking stupid. So how did this happen? Bottom line is people want to kill stupid robots. I mean, it doesn't matter what the story's about. I mean, come on. So they had a very basic program, Seek the Player. And kind of to add a little tension to it, have them increase their velocity like Space Invaders, where you just increase the velocity. They get faster and faster and faster as they're going after the player. And as as they get whittled down, the Robotrons get faster and faster and faster. So it's kind of like, okay. All right. Sorry about that. Okay. A lot of tension there, though. So got the first proto going, and also I was trying to kind of emulate this old game Chase. So I said, no, there's no firing. We're going to keep that firing joystick off just to see if the game was fun, maybe we were done, But it really wasn't. It was fun for a couple minutes, and then I was like, this is like passive aggressive, I can't kill anything, and so needed to bring in the firing. So the firing, so then we did the dual joystick firing. It was awesome. These Robotrons had no chance. Just rubbing them out. The first 10 or 15 we could just kill. And you kind of create an arms race. Anytime you're doing a game development, the more powerful you you make the player, the more powerful the enemy has to become. You need that balance. And one way we could balance it a little bit was to limit the player to 4 shots, which was kind of a nice strategic thing, because if you missed a shot, it would take longer for the shot to respawn. When you killed something, the shot was instantly available. So it also became a penalty for missing. So accuracy was rewarded. So it kind of added a little bit of complexity there. But that still wasn't enough. So we added more grunts. We tried 30 grunts, 40 grunts, 50 grunts, 60 grunts, 70 grunts. It was like, screw it, man, 128. And it was like a binary number. I think that was all the objects we had. So, it's like, maybe it was 127. I think 128 didn't work, but it was pretty cool. And it just like created this incredible mass of robots that was, you come into that screen, and we ended up using this for the 9 wave, 19 waves, 29 waves, all 9 waves. Just this incredible kind of gestalt thing where you appear, you're completely surrounded, and you have like a half a second, like, okay, upper left, go, and really, really awesome. So we had this cool game. Maybe we could have just stopped at that, and put it in the arcade. But it's interesting. A guy, Noah Falstein, has this term he uses: avoid the void. And void varies only in difficulty. So yes, we could have created a game and just made the grunts harder and harder and harder and harder, but that would have been pretty boring. So we really wanted to create kind of a rich soup, a rich, spicy dish with different vegetables and maybe some hot peppers and little surprises. Maybe a rotten anchovy or something. So something entertaining. So the motivation there was, let's create a handful of Robotrons, that each Robotron would add a specific personality, dispatch, movement, offense, defense, and also their projectiles would also be distinct. And this way we could kind of take a few enemies and create kind of an infinite variety, kind of like the game of chess, where I think there's only 6 distinct pieces in chess. And yet you create this infinite variety of play. And that was kind of the goal of Robotron, to really have each character unique and be part of the story. And of course, there's the humans. And the cool thing about the humans is they not only added that human interest, but created a new gameplay goal: the rescue. And so that in Robotron, you want to avoid enemies, but humans, you want to seek out and basically hug them. You want to hug them and and rescue them. And then we threw in inspired by Pac-Man, a progressive scoring, where in Pac-Man, if you eat the ghost, you double your score. In Robotron, we were kind of cheaper than that. We were a little we skimped on that, but you got 1,000 points extra for each one. So after 5 rescues of the last human family, you could have 5,000 points, which in the Robotron economy was pretty cool, because it was 25,000 points for a free man. So if you rescued 9 or 10 humans in a wave, you had a free man. Very, very cool reward for the player. Although I don't know how many times you try to rescue humans, and most of the time you never come up with 9. So really, you're probably killing yourself trying to save the last human family. But for some reason it feels good. The next enemy was the Hulk. The Hulk was inspired, obviously, by the Incredible Hulk. He was kind of a big green guy that was gotten bad moods and strangled people, or I guess ripped everything up. Also, it was inspired by Evil Otto from the game Berserk. Evil Otto was kind of a really bad dude, and he would just basically come out and kill you. And so the Hulk was indestructible, inspired by Evil Otto. He was indestructible. But I felt that just having them come and just kill you and being completely indestructible just didn't seem to be that rich of an interaction. Just like, hi, you're dead. So the Hulk, we created a random walk. So the Hulk would sometimes seek you, would sometimes seek a point away from you, sometimes seek a human, sometimes just walk around at random. And this created this kind of really richness in the Hulk play, where you could be trapped. A Hulk would be coming to crush you, but you never knew at the last minute he might just turn around or turn away. The same as when he was going after a human. He might just walk, all of a sudden just take a left turn. The last little element, which I think really, really made the Hulk, was adding a player interaction. Rather than just a pure indestructible enemy, have your shot affect the Hulk by kind of fending him off for a time. So you could actually, if the Hulk was coming to crush you, you could use your laser to drive him back and escape, or perhaps drive him away from a human that you were trying to rescue. So it was amazingly rich gameplay we got out of the Hulk. The next enemy that was developed to add to the spice to the soup was the Enforcer. Really, the inspiration of the Enforcer was I was getting tired of doing these walk animations. Our graphic system was our programmer art design system was graph paper and colored pencils, and it was getting very, very tedious designing all these animations. And it's like, dude, how about let's make an object that doesn't animate? That's brilliant. And so the Enforcer just kind of floated around. I mean, it's kind of like R2-D2. He just kind of floated around. And the other cool thing about an Enforcer was he was a spawning enemy. So we kind of had this problem in Robotron where you start with all these enemies on the screen, and you get almost kind of a traffic jam. And you get all the action is up front at the beginning, but later on, there's really nothing going on because you've killed all these things. So you kind of end up with this rush hour effect. Too much action in the beginning of a wave, too little action in the end of a wave. And so by having a spawning enemy, which the spheroids were the spawning, the spawners of the Enforcers, you've created this timed release effect. It's kind of like that time release OxyContin. It's really, really cool. Now it balances out the game, and it creates more interest in the later waves by having a spawning enemy. The other really cool thing is it creates a priority target. So you want to shoot the spawners. By killing a spawner, you kill maybe 6 Enforcers. So these spawning enemies were kind of a really cool thing that was a neat innovation in Robotron. The other part of the trilogy of spheroids Enforcers is their projectile, the Enforcer's projectile, which is a spark. And it's funny when I was doing Defender, I was always thinking about clever ways to kill off the player. It's kind of, I guess it's kind of a pastime of video game programmers. It's like, how do we kill these guys off in a very clever and interesting way? And in Defender, developed the concept of a relative shot, which would add your velocity to the projectile's trajectory, such that it would end up where you were going to end up, not where you were, but where you were going to be, which was really, really effective. And in the Enforcer, added kind of a different innovation there, where had a random acceleration, which was added to the velocity every frame. It was chosen. The acceleration was chosen randomly when a spark was created, and then added to it, and it created these curveballs, which were really, really hard to figure out, and it was a range of acceleration, so you never really knew how much a spark was going to curve, or if it would curve at all when it was heading for you. Added kind of a nice little touch there. The other thing was they were non-reflecting. When a spark hit the outside wall of the Robotron screen, the spark would slide down the edge of the screen, which really it was a neat game dynamic, because so often the player, you'd be running around and you'd hit a wall and you'd have to run along a wall to retreat, get away from something, or go for something, and then these sparks would just slide right down that wall, but like kind of a bowling ball, and you were the pin, and very, very lethal. You'd either have to jump up or try to shoot the spark. So kind of another devious thing, and probably the most devious thing of the sparks was the velocity algorithm, where very, very simple thing, where it just took the delta XY between the player and the Enforcer, and I think it just shifted that down by 5 or 6 bits, which created like a divide by 32 or divided by 64. And essentially, what effect that had was the further the shot would get you in the same amount of time, whether it was shot very close to you or very far away. So the further you were from a Enforcer, the spark would be faster. And so really, the further you away, the more danger you were in. So completely non-intuitive, where you really wanted to, you were safer actually approaching the enemy than retreating it from it. But I don't know, I play the game, and I'm always retreating. I mean, it's weird. It's like it's totally counterintuitive. You have to go against your instinct and go for the enemy, and you're safer that way. Here's the enforcer process. You grow up, change your picture as you grow up from an embryo, and then once you're an adult, you go get a velocity, and you go into your loop where you have a certain amount of time before you get your next velocity. If you time out, go get their new velocity, and then every so often you decide to take a shot at the jag-off down there at the end of the screen there. And kind of a Chicago expression. Anyway, and then you sleep 3. So back to the loop. So it was a 20 hertz process between updates of the enforcer. Brains were the next enemy, and finally had to kind of get back and do some animation. And I mean, there was a problem. This was kind of worrying me because Robotrons were supposed to be the most intelligent beings ever created, and all the enemies so far were really stupid. So I just said, well, I have to make an enemy that's really smart, and maybe if it isn't smart, maybe it just looks smart, you know? And so put like a really big brain on it, which actually just made it easier to shoot them. But, you know, it was interesting. So the brains, the cool thing about the brains is they seek out the humans, which they reprogram into these things called progs, which were the zombies of that era, and they were kind of dangerous in their own right. And by reprogramming the humans, they eliminated your scoring opportunities, and the brains kind of to add to this mix of these Robotron characters. The inspiration was to feature different enemies in different waves. If all enemies appeared in all waves, it would have been kind of a monotonous game. So the idea was featuring different enemies in different waves, and the brain waves were featured every 5 waves. And you would have a huge number of brains, a huge number of humans, and this would give you this huge scoring opportunity, this huge kind of risk-reward opportunity to get just a massive scoring if you could kill the brains and get all the humans. The brains had this pretty nasty projectile, which was known as the cruise missile, which was the only projectile that would constantly seek the player, but it was kind of a random seek where it would seek kind of an offset about the player, so that it just kind of stuck around and was, bothering you, kind of like a mosquito or something, always following you around. A very, very nasty and interesting projectile. And then the last thing about the brains is there was this thing called the Mikey bug. I don't know does anybody here know about the Mikey bug? Okay, wow, okay, that's cool. Basically, the Mikey bug, I found this out several years after releasing the game, but at the beginning of a brainwave, all the brains, due to a initialization error, they're supposed to seek out the nearest human. They all seek out Mikey, and so they're all going after Mikey. And so if you can keep Mikey, you don't want to rescue Mikey, because once you rescue Mikey, then they'll go after everybody else. So you have to keep Mikey alive, not rescue him, and fend off these brains. And if you can, then you have this huge bonus opportunity of rescuing all the humans, generating massive, of course, sometimes over 100,000 points, 4 or 5 free men. And but the other thing that's really crazy about it is that while you have to keep one enemy alive. Or the wave will end. And so as you're killing all these things, so often, you have this massive opportunity to save 20 humans, but then you get off one last extra shot, killing the last enemy, and boom, it's just all gone. It's all taken away. So It's an amazing thing, and it's. But this is not programmed in the game. Just a bug, just a kind of emergent behavior of the Robotron code. And some of the coolest features of the game are bugs. It's better to be lucky than good sometimes. But you have to have the skill not to make the program crash. To be buggy enough to have richness, but not actually crash. I mean, although there is a bug, the diagonal shot bug, which we won't talk about that one. That was you kind of get the that one. Basically, you shoot your bullet into the program stack, and is not. And you get kind of what we call the carpets, the initialization code. But actually, that was fixed at one point. Okay, we had this rich tableau of enemies, and holy shit. So we had one last enemy to do, and this was the tanks. And the tanks, the cool thing about the tanks is they were really nasty. We needed like this paywall in the game, the final paywall to relieve the monotony. And so the tanks would shoot these bank shots. Basically, they would decide whether to aim a projectile directly at you or bank it off a wall. This was the only reflecting projectile in the game. So it was a new thing, and players weren't used to this. And it only came up like once every 5, I guess started in wave 7, 12, and 17, and so forth. And, or maybe it's only every 7, I don't remember. But it creates this huge challenge and just massacres maybe 5 or 6 men that you've saved up. Really, really a challenge, and kind of helps that roller coaster of challenge and then relief as the game gets easier. So that was kind of the icing on the cake there with the tanks. And we talked about some of the AI. Really, the AI in Robotron is use random numbers really to create kind of anthropomorphic AI, where you think they're a lot smarter than they really are. It's amazing how that works. We had some really cool graphics, and the effects are really awesome about Robotron. Explosions, horizontal, vertical, diagonal. This really cool player materialization effect, which kind of starts the wave and shows you what's going on, and a cool wave end wipe effect. Coolest attract mode ever. Let's see Robotron. Ouch. Let's see if we can get to a brainwave. Okay, thank you very much.